Okay, this video is going to introduce you to the concept of extrema and in calculus. And when we refer to extrema on a graph, we are talking about simply the maxes and the mins. Now, this isn't entirely a new concept. It's a very visual concept, so you already know how to find it if you're looking at a graph. I want you to think about, eventually, this is just going to be more the graphical perspective of it, but then as we get into the second half of this lesson, it's going to be more, how do I calculate or how do I find the extrema? And that would be either using your graphing calculator, which you've done for years, probably since Algebra 1 for sure, and Algebra 2 you did this. But how did they used to do it before the days of graphing calculators? That's kind of what we want to put ourselves into the mindset of, is how could we do this without a graphing calculator? And I'm going to take you back to how I introduced extrema and this whole chapter really with curve sketching. We talked about a parabola and how we have an equation to find the vertex point, which is an extrema. That's either the lowest point or the highest point. And that's great, but that only works for a parabola. So the question is, what about all the other polynomials and then all the other functions beyond polynomials? Okay, and then of course we have different types of extrema. So let's just clarify. Let's move these guys down. Two types of extrema. Let's get those on the table, so to speak. So we have our relative or local, just two terms that mean the same thing. And then we have our absolute or global extrema. So we've been talking about, and I might not have been as specific as I should have with my terminology. When I've said maxes and mins, I should have always been using the word relative or local. That's really all we've talked about so far. Incidentally, your textbook actually presents it in reverse order. And when we get to the concept of absolute or global extrema, we need to start to think about like the actual highest point on the graph or lowest point on the graph. And the only way we can do that is to actually compare y values. So let's just take some functions that we're familiar with. And my parabolas are one function that I'm familiar with. So we'll keep those parabolas on there. And then let's just go ahead and sketch maybe another function that we're pretty familiar with would be a cubic function. And if we start to look at these, the parabola has a minimum and a maximum, but then the ends keep going forever. So the first graph there has what we would call an absolute minimum. That would also be a relative minimum, but we can say that's the lowest point for sure on the graph. It doesn't have any maximum because it goes up infinitely at either end, and not really an end. And we can't say what the highest point is that it reaches. And then the reverse for the second one, we have an absolute maximum and no absolute minimum. And then this one, we have 2 points that I think we would casually refer to as, hey, that's a high point or a maximum. And then we've got a low point or a minimum. And those we're going to put the word relative with. And the reason is that my graph goes up forever on the right end point of my cubic here, and then down forever on the left, I shouldn't even say left end point, left part of its domain, as x approaches negative infinity. So the graph is going to go infinitely up, and we're never going to know what the highest point is. We'll just keep going. But this point here is considered a relative maximum in that area, and then relative minimum. So I want you to consider another graph, maybe like I don't know what that would be, 1, 2, 3, 4, 5 turnarounds. So a 6th degree polynomial, or of course it could be a higher than 6th degree polynomial. And now I have several relative maximums. So I've got a relative maximum here, a relative maximum here, and a relative maximum here. And then the question is, what's happening? Well, how do I know which one's the highest? Well, obviously, if I'm looking at the graph, there we go. That would be my absolute max, that particular relative max. So the only way I know that is by actually comparing the y values, if I'm pretending there's a coordinate graph there and that this is actually graph to scale. And then I know that's the highest point. If I don't have that, so let me take you to the method that we've been using to find our relative extrema, what I've kind of drilled into your head. so to speak, is our number line test. And we find our points where our derivative is 0, and then we figure out our sign of derivative. And our sign of our derivative might be, let's say, negative, and then positive, and then negative. And that tells me my function is doing this. And that has allowed me to find relative maximums. I know there's a maximum here, and then I know there's a maximum there. But without comparing y values, I have no way of knowing which one is the highest. I can't even really go with, oh, this is a longer section here than the increase, for instance, because it depends on the rate at which it's increasing. So suffice to say, we just don't have enough information there to get absolute. So for that reason, we're going to kind of abandon that method. And here's why I decided to do this second. What I found is that if I taught the absolute extrema first, students understood it, did great. And then as soon as I showed them the number line, they never, ever went back to what we call, it's commonly called a candidates test. I call it the table method for finding absolute or global extrema. It's very intuitive. We're literally going to be finding y values at specific points. We don't want to just randomly be finding y values. We don't want to just go to our table and just search our table because we might have fractional values. So we need to figure out which points to consider, what would be my possible relative extrema, and then just compare those. So it's possible you could use a table in combination with that, but it really just becomes an extra amount of work. And I don't care at this point, everything my function is doing. I just want to find the maximum point. So I don't mind if you do, just to kind of make more sense of this, but we are going to go to, just as a visual, we're going to go to a table method of, here's the points that I'm considering, and then I'm just going to find y values and compare. And literally the highest one is going to be my maximum, and the lowest one is going to be my minimum, and these are going to be absolute. Okay, this will all make a little more sense once we do an example, obviously, but I just wanted you to have kind of a preview and sort of in your head, how's this different? Because, hey, we've been finding maxes and mins. We sure have. But we haven't been comparing our multiple maxes or mins to say which one's higher. Okay. Before we jump into an example, I just want to pose the question of, when can we, if ever, guarantee that a function will have both an absolute maximum and minimum? Can we guarantee it? And hopefully you're saying, no, we can't, as long as we're working on the entire domain. However, now let's consider one slight modification. Let's say we're working on a closed interval. So not negative infinity, positive infinity. We pick an interval, and it's a closed interval. Now can we guarantee that the function has an absolute maximum and an absolute minimum? So the answer is yes, as long as common prerequisite that must happen, and that is we have to have a continuous function. So we call this the extreme value theorem, and this note sheet is posted for you, or on the back side of your copied note sheet with all of our information about that we've been using to connect f prime and f double prime. So I think this will be a helpful note sheet for you. We already went through the top part, so let's jump into extreme value theorem. I've got some nice visuals here that I want to take a look at. And this just kind of shows you how a function can have, as soon as we talk about a closed interval. So we're now starting and stopping the function. And this could still be a cubic function. I'm just looking at a section of it. And it could be that we have a maximum and a minimum, and those are both kind of my turnaround points. It could be that my function is decreasing the entire time, and my maximum and my minimum are both endpoints. Or it could be a combination. So the third graph you see here, I'd say the minimum, absolute minimum, so we have two relative minimums, but the absolute is going to be this one on the left. The absolute minimum is an endpoint. The absolute maximum is an interior point, a turnaround point. And this one would still be a relative minimum. This would be both an absolute and a relative minimum. So it doesn't take away the classification as a relative minimum. It's just like the absolute minimum trumps the relative minimum. It's superior as far as a description. And then the exact opposite on this last graph here, we have the absolute minimum is an interior point, and then the absolute maximum is my right-hand endpoint. So I think that if you look at those examples and think about the points we're comparing the turnaround points and the endpoints. So that's exactly what we're going to do. Now let's remind ourselves of how we find these points. So how do we find points like this? Not the endpoints, because the endpoints are just going to be whatever interval I have. How do I find points like that? What's special about those points? Yeah, those are the points where my function has a slope of 0, my derivative is 0. We call those critical points. So our method I've got in this lovely box, and I'm actually not going to go through that right now, but if you ever hear me saying, nope, that's not you're doing the relative extrema test, you got to use the absolute extrema test. This is the table that I was talking about, and we'll just go through that as we do an example. So join me on the examples and we'll make sense of this. But I did have one more thing I wanted to say before I get to examples, because there's a few questions I'm going to ask you in your My Math Lab assignment on this. If we don't have a continuous graph, then we've got to be careful. So let's just look at a couple of these graphs and what could happen. So I'm going to change one slight thing, and that's going to be, let me clean up my graphs slightly. Okay, so if we take this graph that we have, I'm just going to go with this one over here, and I make this an open circle. So there's a point of discontinuity there at x sub 2. Then what would have been the maximum point is now no longer a point. So my function's like approaching this high point, but we don't know how high it gets. It gets like really, really, really close, right? There's a limit of some value as I get up to that point, but I'm never reaching it. So therefore, I say that there is no absolute max. So that extreme value theorem only guarantees for a continuous function that there's both an absolute maximum and minimum. And then same thing, obviously, if this was an open circle, then there'd be no absolute minimum. We couldn't say that this, let's say that's a closed in, we couldn't say that this right-hand one is an absolute minimum because the graph gets lower over here than it does there on the right-hand side. So it'd be the same thing, no absolute minimum. And you can kind of see with the other ones there, we could do something like this, and then we'd say that there's an absolute minimum, but no absolute maximum. So I will be asking you a few graphing questions, and you can make sure that you understand those concepts.